obtuvo el título de Bachelor in Science en Ingeniería Física, y también al mismo tiempo hizo un Bachelor en Filosofía. Después obtuvo su doctorado en la misma institución, en la Universidad Católica de Louvain, en Ingeniería Física, y después de eso hizo varias estancias, incluyendo MIT, Cornell, en Bolonia, en el Centro de Supercómputo. Y desde 1998 es miembro del FNRS de Bélgica y es full professor a partir del 2011. Tiene una gran trayectoria en su investigación en el área de carbono a la nanoescala y otros materiales nanométricos. Y algunos de los reconocimientos que ha recibido, que son los más importantes, él ha sido 2 veces ganador del Premio de Física de la Academia Real de Bélgica, es miembro fellow the Academy of Sciences for the American Academy for the Advancement of Sciences desde el 2013, y bueno, tiene una gran cantidad de publicaciones, más de 15,000 citas en su trabajo. Entonces, bueno, sin más preámbulo, le damos la bienvenida al profesor Jean-Christophe Charlier.
Muchas gracias, Andrés, for the introduction. I will switch to English. Sorry, I'm not a Spanish speaker. Oops. Thanks to everybody for coming. So the title of the presentation here will be Ab initio modeling of 2D materials, and the outline is the following. So I will briefly mention the type of ab initio modeling that I will be using, because it has already been introduced by Andrés Botelho yesterday during the nanoscience school. I will briefly also introduce the 2D world, and I will focus mainly on 3 points during the talk. So a novel material that we have recently investigated theoretically, and 2 effects also that are quite interesting in graphene, and that actually the first one has not still been experimentally observed. The second one has been, in fact, in this case. Okay, so let's first focus on the modeling part. So in fact, in this talk, I will mainly focus on the density functional theory formalism, which is a theory for non-interacting electrons, which are in a cone-champ potential. So you have the cone-champ potential that is here, and this cone-champ potential contains the external potential for the electron, the RT term, and also an exchange correlation term, which take into account of several quantum interaction. And the way we work, in fact, is that we use a trial density, which is really the most important variable in this theory, and we construct the cone-champ potential, and from this cone-champ potential we solve the Schrödinger equation to get the wave function for the particles, and then we can reconstruct, in fact, the electronic density. We have, in fact, implemented this framework in a code that is developed in our university in Louvain, in Belgium, which is called Abinit. So you could go on this website and have a look at this code. You can play with it. There are lots of tutorials, so you can really enjoy using this DFT code. We can calculate with this code total energy. We can optimize the atomic structure that we are investigating. We have access to electronic properties, to charge density and spin, and also when we go to density density functional perturbation theory, we can have access also to the vibration of the atom in the solid, so with the phonon spectra. It allows also to go beyond DFT when we investigate excited states, for example, and mainly we can have band gap correction, because with DFT there is a clear problem in the prediction of band gaps, so you have to correct them, and also if you want to have access to excitonic effect, you have to solve the Bethe-Salpeter equation. But this is not the main part of the talk here. So now I will focus to graphene. So you know perfectly graphene for sure. It's a recent 2D material that has been synthesized for the first time in 2004 by two physicists from the Manchester University. So it's a honeycomb lattice, so you have an hexagonal lattice with carbon atoms. It's a 2D materials, and I will introduce this family of 2D materials because they are extremely interesting from an electronic point of view because all the electrons are confined in a single plane. So this is the case for graphene, of course. And so if you look at the electronic properties of this system, you have the band structure here, and if you look at the K point in the reciprocal space, so this is the Brillouin zone, the hexagonal Brillouin zone of graphene, you have the K point, and if you look carefully here, you have a linear dispersion for the electronic bands in this system, which is quite unusual in solid state physics. And this linear dispersion allows to mimic, in fact, a kind of Dirac massless fermions in solid states, and so you can use this type of Dirac Hamiltonian to really mimic the system in this situation. And so graphene has been studied quite a lot because there are lots of new phenomena that appear in this 2D system, like, for example, Klein tunneling in quantum transport, but also half-integer quantum Hall effect, and so on. So this is a very interesting materials, but there are lots of others that has been also investigated. So mostly, for example, boron nitride. So boron nitride is exactly the same as graphene, except that well, I forgot to mention that in graphene you have two sides in the unit cell. You have two carbon atoms, but you have one which is blue and one which is red, because in fact they are not on the same triangular lattice as you can see here. So you have these three red and you have these three blue. So you have a new quantum numbers that can be associated to the wave function, which is called the pseudospin. And this pseudospin is quite important to, in fact, investigate theoretically the electronic properties of graphene. In the case of boron nitride, you do not have two, you still have two atoms per unit cell, but they are not the same. So you have one boron and you have one nitrogen. And the fact that you just change the nature of these two atoms leads to a complete different situation. So here you see that from the electronic point of view, you have a clear insulator with a 5.56 CV band gap. So the electronic properties are completely changed just by modifying the nature of the atoms. So in fact, in a simple time binding picture, if you just modify the on-site energy of these two atoms in the unit cell, you will get directly this band gap. Okay, so this insulator material, 2D insulator materials, is frequently used either in bulk or in few layers as a substrate for graphene. Because graphene, when you put it on for example, on SiO2, is corrugated and induces some electron and hole puddles in the structure, which induce some scattering, in fact, in the transport properties of graphene. But when you put graphene on this ultra-flat substrate, you have extremely high mobility for your charge carrier, at least one order of magnitude compared to what you can obtain, for example, in SiO2. However, when you put it on HBN, you have this moire structure that you can see here. So a kind of super lattice that appear. This is because, in fact, you do not have exactly the same bond lengths in the two structure. So you have 2.46 in graphene, and you have 2.51 in BN. So you have about 1% of difference. But this leads to this superstructure, which can lead to very interesting also electronic properties, and various novel quantum phenomena has been observed, like, for example, fractional quantum effect, and also Hofstadter butterfly, for example, which has never been observed before on solid-state system. Another examples are TMDs, and TMDs have already been introduced by Anna Laura yesterday in the nanoscience school. So they are mostly layer plane like this, which have a certain height in this case, where you have a metal atoms, which is the M here, and a chalcogen, which can be, for example, sulfur or selenium. And in this case, you see that most of the structure are semiconducting, but what is interesting is that when the material is a bulk system, so you have a stacking of this plane, you have an indirect band gap. But when you come to a single plane, you see the band gap becomes direct. So this is extremely interesting for example, optoelectronics devices. And in this material, since you can in fact have very heavy materials like tungsten, the spin-orbit coupling becomes very important as well. So in fact, in this situation, you split, you see, for example, you have a split here of the valence band, which is of the order of a few hundreds of milli-electron volts, and about tenths for the conduction band. So this also introduced some modification of the electronic properties compared to other 2D systems. And this is very interesting for optoelectronics, again, because in fact in this system you have a broken inversion symmetry in the case of a monolayer. So this means that in fact the K point and the K prime point of the Brillouin zone are no more the same. So due to the spin-orbit coupling, you see that, for example, the valence band are no more degenerated, but you have spin up and spin down for the K minus point, but you have the opposite at the K plus. Okay, and so if you use, for example, a circular polarized light, you can, for example, excite specific spin up from the valence band to the conduction band, and if you use the opposite circular light, you can, in fact, excite another type of electron. So you can really play with not only the spin of the electron, but also the valley, so the dependence on the K and K prime of the Brillouin zone. So there are lots of new physics now in optics, mainly on this 2D system. Another example, phosphorine. Phosphorine comes from black phosphorus. So black phosphorus is quite well known. It's a lamellar material, so you can also extract a single layer. This is also a semiconductor. And what is extremely interesting in this case is the fact that the electronic band gap of the system depends on the number of layers. So you can go, for example, from a monolayer with a 1.6 EV band gap to the bulk material, which is about 0.45 electron volts for the band gap. So you can really play with the number of layers and have a different band gap depending. And there is a kind of empirical law to get the band gap from the number of layers that you have in the system. Silicon, germanium, and tin can, in fact, are also interesting materials, and the 2D materials corresponding to these three atoms are silicene, germanium, and stannine. So it looks as if they are close to graphene, but it's not the case. They are little buckles. So it's a bit like phosphorine. Phosphorine is puckered because in this case you had 5 3D electrons, so it favors sp3 hybridization compared to graphene, which is sp2 hybridization if you take the chemistry picture. So you have this puckered material for phosphorine, and here you have a kind of buckling of the plane. This is because silicon-silicon bond is much more important compared to the carbon-carbon bond. And in order to maximize the overlapping between pi electrons, in fact, you need to have this buckling in the plane. And the buckling is even more important for germanium and for stannine. But you see, you conserve this linear dispersion here close to the K point, which is similar to what you observed in graphene. But in this case, again, if you take into account, if you switch on the spin-orbit coupling, you will observe that you have the presence of a band gap in the system, and you can really control that. Okay, there are lots of many more 2D systems, but I have no time here to represent all the family of 2D materials that has been already proposed and investigated. But the main point is that if we want to have access to a lot of optical device and with different optoelectronic properties, we need also to have a very large range of band gap. And this is really the case, as I just briefly mentioned in the introduction, of all this system going from graphene with no band gap to silicene, germanium, stannine with a very small band gap, black phosphorus for about 0.5 eV to 1.5. The TMD is from about 1.5 to 2.5, and you have also the hexagonal boron nitride, which is at the far value for the band gap. Okay. As it has been mentioned yesterday by Andres, now with all these bricks, we can really construct materials with a control, with a perfect control of the different layers. So we can stack all these properties, all this system, in order to control and understand a specific and get a specific properties for the stacking. So this stacking is now metamaterials, like a bit a jelly cake like this, where you have different materials with different properties. And what we have been what we have been investigating in the last few years is the fact that it's more than a combination of the properties of the different materials. It's a kind of more important and synergical properties that you can obtain from this stacking compared to the different layers. So it's very important, and also the fact that you have more and more 2D materials can lead to even more important number of possibilities for this stacking. And so the first example that I would like to present you is Borophene. So Borophene is a new type of 2D material that has been recently synthesized by the group of Mark Sam in Northwestern University. And in fact, what they did is they synthesized Borophene by atomic deposition, as you can see here. So it's molecular beam epitaxy, and this is performed at about between 500 and 700 Celsius on a silver substrate. And they observed the formation of a kind of flakes of boron, pure boron materials, and they investigated this using STM and also STEM. And they proposed a model for this Borophene structure. So the Borophene structure, as you can see here, has a triangular lattice like this, and it's a little bit buckled, as for example the case of silicene and germanium that I showed you just before. So these STEM pictures have clearly shown this buckling, and in fact, when you look from the top, you have a perfect agreement between the STM image that you obtained experimentally and from the atomic model here. A few months later, a group of Chinese researchers have also shown that it was possible to synthesize with different temperature and different deposition rates other type of boron structure, and very recently they were even able to make the analogous of graphene in the case of boron. So a perfect hexagonal structure, but mainly only composed of boron atom in this case. But in this case, it's no more on a silver substrate, but it's on aluminum, and probably from calculation, in fact, there is a very strong charge transfer from the aluminum substrate to each boron atom of about 1 electrons, which clearly stabilize the structure. So probably the structure is not really stable when it's isolated out of the substrate. So the main message is that for boron, in contradiction, for example, to graphene or other 2D materials, you have really a lot of polymorphism. So you can start from the triangular lattice that I show you with this buckling, and if you extract, in fact, boron atoms, you can go to different situations until you go to this honeycomb system. So when you have only one atom of boron on the hexagonal lattice. And from theoretical calculations, so there are really 3 phases that are more stable than the others. So one is the triangular here. You have this beta 12 and you have this X3 here that are the most stable compared to the bulk system. So in fact, the bulk system for boron is this one. So it's a little bit complicated. Boron is really a very funny materials to investigate. So you have clusters of borons which are connected to each other to form a 3D system. So it's quite interesting. This is a more stable 3D phase. And in fact, for example, the triangular phase is about 0.55 EV per atoms less stable compared to this bulk material. But we have investigated this system, this 2D system, and especially the electronic properties. So we have calculated using ab initio technique the band structure, and you see that if you look at the band structure, you have very strong dispersive bands which are crossing the energy, the Fermi energy, which is here, and these bands that are quite dispersive here, are not present, so are only present along the Kx direction of this Brillouin zone. So along gamma x, as you can see here, but also along ys, which is here, but not along, for example, gamma y or xs. xs there is nothing, and gamma y there is nothing as well along. So you have a clear anisotropic behavior of this system regarding its electronic point of view. And so in fact this means that probably the transport will go only along the Kx direction, but I will come back to this later. So we can also calculate the Fermi velocity for the charge carrier at the Fermi energy, and we see that we are at 6.6 10 to the power 4 meter per second, which is about 1/4 of what we can obtain, for example, in the case of graphene. So this means that it's a really normally a very good metal that you with this Borophene. So this is the Fermi surface. So the Fermi surface of a 2D materials is just a 2D line, in fact. And this is the 2D line of the Fermi surface. So you have a clear vector which will induce a k vector that will induce transport along the kx direction, but you will not have along the ky direction. So you have a kind of threshold angles with the maximum with a kmax value, which is here, in fact, which goes to this point between y and s, which allows transport. The transport will be clearly anisotropic in this system. So now we want to investigate also optical properties of this system, and so the interaction of a photon with the charge carriers in the plane, and especially with a specific electric field with a certain orientation. So you have a certain polarization for your light, and we are going to look at that using also a model. So we calculate the dielectric function, and in the case of a system like Borophene, in fact, we have to take two terms, an interband terms, which come from a transition of electrons from one band to another, but also due to the fact that it's a good metals, we should also introduce Drude models in order to take into account of intraband effect in this dielectric function. Okay, so the dielectric function is composed of a real part and an imaginary part here. And if we want to calculate the optical conductivity, we use this formula, and you have imaginary numbers. So if we want to have access to the real part of the optical conductivity, you need to use, in fact, the imaginary part of your dielectric function in order to get this optical conductivity. Okay, so I don't want to go into lots of technical details, but this interband contribution come from, you can really look at the band structure if there are some transitions that are possible in Borophene, and the second part coming from the Drude models are in fact here, and especially for the imaginary part of the dielectric function, and you have to introduce a relaxation time which leads to an electronic mean free path, and this electronic mean free path corresponds to the distance that can, in average, can travel the electrons between two scattering events. Okay, for the rest I don't want to explain, it's too technical. Okay, so if we want now to calculate the optical conductivity, let's start with graphene to see if the model works. And you see this is the curve that we obtained for the optical conductivity in graphene, and this is the transmission, the corresponding transmission that is calculated. So we have about 96% of the light that is transmitted when it goes through a single plane like graphene. And this is what is experimentally measured. So this is the optical conductivity, and you see that we are in quite good agreement with what is measured experimentally. So you have this plateau here, which come from mainly, in fact, of interband transition at the K point. So you have electrons that can go in the linear dispersion. You will get this plateau here due to at the K point, and this peak mainly come from the M point of the Brillouin zone, so which is at the center of each segment of the hexagonal Brillouin zone, and there are some possible transition as well, but at higher energy for the incident light, so around 0.4, around 4 to 5 electron volt. And this is what is also observed when you put graphene under an optical microscope. So you see that the light is completely transmitted when there is no graphene. When there is graphene, you have a decrease of 2.3%. This is what we observed here. And if you put another layer, you will get 4.6% of decrease for the transmission. So the model seems to be in good agreement with what is observed for graphene. So what about Borophene? Can we predict something about the optical properties of this system? So we start with an incident light where the polarization is along the x-axis, since the material is anisotropic, so we have really to check if there are some differences between the x and y axis for the polarization of the light, and that's what we observed here. So this is a blue curve compared again to graphene, which is still here. So you see that there is nearly no conductivity, optical conductivity in the visible range. If we look at the polarization along Y, we see that it's clearly anisotropic in the UV. So you have a completely different response in this case. And since you never know experimentally if you will be in the Y or X direction, mostly you will get an average of these two, and you have this black curve that is here. And so if you take this black curve, we see that until we reach 3 electron volt, we have nearly no optical conductivity. This is because in the electronic band structure, you do not have any possible transition except when you are above 3 eV. And in this case, you see that it's completely transparent before. But this is without taking into account the fact that Borophene is a metal. So you have really now to take the contribution of the Drude model for that. And we are trying to increase the value of the electronic mean free path in this model in order to go from a bad metal to a very good metal. So if we improve the electronic mean free path from 1 picometer to, let's say, 100 nanometers, we will go to a bad metals to a very good metals. And you can see what's going on when we increase the value of this electronic mean free path. You clearly see that we still keep I come back again. So we increase, the transmission goes down, here the optical conductivity goes up, and suddenly it goes down again, and the transmission also goes up to 100%. So this is quite surprising, but the point is that for a value which is probably close to a good, which is the case for good metals and which could be potentially attributed to Borophene, in fact, we should have normally a value of 100% of transmission, which is clearly higher than what you can observe in graphene, for example. We have also checked for the two other phases that are quite stable, and we observed also, well, it's not so great, but we still have a better value for the transmission compared to graphene. So this is a very interesting materials because it is both conductive and also it's clearly transparent. So this is a kind of material that it's really infrequent to find in nature. So this is the take-home message. So we have investigated using ab initio technique electronic and optical properties of Borophene. Borophene is polymorphic, but mostly metallic with high electronic velocity. The full anisotropy of its electronic properties has been analyzed with the Fermi surface. Borophene is found to exhibit extremely low optical conductivity with the absence of interband transition up to 3 eV. There is a strong optical anisotropy in the UV range, and we have computed transmittance which possibly reach 100% in the visible range, making Borophene more transparent than graphene. Okay, so this was an example for one novel materials and the way ab initio technique can really predict and helps probably experimentalists to find novel properties in this 2D system. Next topic will be dedicated to optical Hall effect in strained graphene. So this is an interesting effect that we proposed in strained graphene, and that is actually not observed. So if there are some experimentalists that are interested in finding this effect, we could discuss during this week. Okay, so let's first start with an introduction. Probably you all know what is Hall effect. So the Hall effect is when you pass a current through a sample, in fact, and you apply a very thin film, and you apply a magnetic field like this. In fact, what you observed is that you have a Hall voltage that is present on both sides of the sample. So you have clear current that appears, and you have what is called a Hall conductivity that appears, which is perpendicular to the normal conductivity that is along this transport direction. So you have sigma xy, which is different than sigma xx in this sample. So each time you apply a magnetic field like this, when you have a current, you get this Hall conductivity in your sample. Now some reminders about optical effect. So if you shine a sample with an incident light with a certain polarization, you can have either a reflection, you can have also absorption and transmission of this light. Now we are going to combine both effects in order to have the optical Hall effect. So this is what we do here. So we have a sample where we apply a magnetic field, and we have an incident light with a certain energy and a certain polarization. Okay? If we do that, in fact, we have what is called the Kerr and the Faraday effect. So the Kerr effect corresponds to the reflected light, and the polarization has been rotated due to the presence of this magnetic field. That's the same in the transmission of the light. You have the Faraday effect, where you have also the polarization of the light that can be, in fact, rotated due to the presence of this magnetic field. So you can clearly have access to this transmission of the light throughout the sample just by having access to the optical conductivity in the system. This optical conductivity depends on the energy of the light and also on the magnetic field. And you take the real part of it in order to get this transmission. On the other hand, the polarization rotation here is directly proportional to the real part of the optical Hall conductivity, so along xy, which is also dependent on the energy of the incident light and on the magnetic field. Okay, so this effect have really been observed experimentally. So if you shine a graphene layer in the presence of a magnetic field, you can really observe the presence of a rotation of the polarization of this light throughout the graphene, and it depends on the incident energy, as I just mentioned before, and also on the applied magnetic field. So you have this different curve which show this dependence on the magnetic field. But in our case, we do not want to use a magnetic field. So this magnetic field in the system, in fact, leads to a time reversal symmetry breaking, which induces this optical Hall effect. Okay? In our case, we want to suppress the magnetic field, but we want to use the strain instead in order to produce the same effect. So the strain in graphene induces a lattice symmetry breaking instead of time reversal symmetry breaking of the magnetic field. And in this case, you could also have optical Hall effect, but without the presence of a magnetic field. Okay? So let's have a look at the situation here. So this is a flake of graphene. We have a specific direction that we will take as the referential direction. So this is the armchair direction of graphene. So this is this one. We have a certain light that arrives on graphene. So you have electric field, magnetic field here. And so, in fact, you have this electric field for the polarization. So you have this phi here, which is the polarization orientation, compared to the referential direction, which is here. And you have also the energy of the incident light, which is important in the model. Okay, and now we strain graphene along, for example, an aleatory direction, which is here, with a theta angle, which is here, and with a certain amplitude, magnitude, which is epsilon here. So we have 4 different variables in this model. So the frequency, which leads to the energy for the incident light, the polarization direction, the magnitude of the amplitude, and the direction of this strain in graphene. And we use also, again, density functional theory and also tight binding methods to calculate the optical conductivity and the optical Hall conductivity in the system. And so if we do that, first without the presence of strain, so you see that we get, you remember the curve that we had in the case of Borophene, we still conserve that for the same curve for graphene here, for the optical conductivity without strain. And you see that the optical Hall conductivity is, of course, 0 because we do not impose any strain, so there is no lattice symmetry breaking in the system. You see that we have a very good agreement between DFT calculation and the tight binding model, so the linear curve and the dash curve in this study. After that, we impose a certain strain. In this case, it's 8%, and it's a certain direction for the strain. It doesn't matter. And what you see is the strain induce some peaks peak splitting. In the sigma XX, so in the optical conductivity. And this is quite interesting. And also, strain induce non-zero value for the optical Hall conductivity in your system. So it's no more zero, it's clearly positive and negative here. So you clearly have the possibility of tuning the energy of tuning the optical Hall conductivity from positive value to negative value, depending on the energy of the incident light. So you clearly see that it's a quite interesting system because it will depend on the energy of the incident light. Okay, so if we look more specifically these two, we have tried to modify the direction of the strain, the direction of the polarization of the light for a certain magnitude of strain, and you see that in fact the peak position in the optical conductivity depend directly on the direction of the strain, but not on the light polarization. So the blue and the red curve are exactly degenerate here. This is not the case for the optical Hall conductivity, so which depends, as you can see, strongly on the direction of the strain, so theta, but also on the light polarization. So you see that when you change from minus 45 to plus 45, the value of phi, you get completely two different curves, which is not the case here in the optical conductivity. Okay, so sigma xy, so the optical Hall conductivity can be reversed just by tuning theta and also phi, so the polarization of the light. So, as I mentioned, a magnetic field can lead to optical Hall conductivity, but the strain as well. And this optical conductivity is much more rich because, in fact, it depends on 4 different parameters. So, the energy of the incident light, the direction of the polarization, the direction of the strain, and its amplitude. So it's quite a rich model which is induced by this latest symmetric breaking. And where does it come from? In fact, if you strain graphene, you will not get anymore an hexagonal, perfectly hexagonal Brillouin zone. So the K and K prime points are no more equivalent in this case. And also the M1, M2, and M3 points, which are at the center of this segment of the Brillouin zone, are also completely different due to the strain and depending, of course, on the direction of the strain. So when we calculate using the Kubo formula the optical conductivity in the system, we see that for the optical conductivity, we always have positive value for the optical transition function. So that's why sigma xx is always positive. Okay? Of course, you have different values, you have different peaks due to the presence of different maxima in the Brillouin zone on the different value of m in the system. On the other hand, if you calculate the optical Hall conductivity, so sigma xy, and you look at the optical transition function corresponding to this Hall conductivity, you see that you can have both positive values and negative values in the system depending on the M point. So for example, for M1 it's negative, for M2 it's positive, and M3 again it's negative. So you can explain just by investigating this optical model why you have this variation in the optical Hall conductivity. So we have played a lot on this model for different strain angle, for different polarization angles. Sometimes we have 3 peaks that appears when we have really 3 endpoints that are completely different for a certain, for example, strain direction or for a certain polarization direction. So it's clear that in fact sigma xy is strongly dependent on both light polarization and also strain direction. Yes, sure.
What happened if you use circular polarization?
We did not do that. Yeah, I don't see what you should observe in the case of circular because you do not have any more this rotation, so I don't see of the field that is different, right? Well. I'm not sure, but normally you should also observe some effect in the sigma xy, but I don't know if it's so easy to explain than the linear polarization, in fact. Because in that case, you cannot really define a phi value, right? in the circular polarization. So I don't see how you can introduce that in the present model. We did not do that anyway. Okay. And then we also look at other specific strain effect in sigma xy. For example, we check that for high sigma xy peaks, even for small strain, we have only a few percent. You see that only for 2% of strain here, you still have this peak. So this phenomena is something that could be normally observed even for a very small strain in the system. It's also sigma xy is also very important when you have not only a single layer, but if you have a few layers, you could also observe, and especially if they are randomly oriented, you preserve the Dirac cone, and in that case you should normally observe a stronger effect in the system. And also we investigate the case of shear strain, and shear strain in fact are required to get the same effect. Smaller shear strain are in fact required to get exactly the same effect. So you have for 6.8% of uniaxial strain, you need in fact about 4% of shear strain. So this is clearly also an interesting situation. We have tried to use this model also for other type of 2D materials like borophene, silicene, and phosphorine, and we see that the sigma xy is also a very complicated. So we are still in investigating this type of curve because it's quite chaotic and it's very complicated to explain. But anyway, when you apply strain on these 2D materials, you also observe this kind of optical Hall conductivity. Okay, with that I finish the 7th point, the optical Hall effect in strain graphene. Strain engineering can be used to achieve optical Hall effect under zero magnetic field. High value of sigma xy for small strain with appropriate energy are predicted. Value of sigma xy can be reversed by tuning incident light and also strain. And it's a general technique to achieve optical Hall effect in other 2D materials. And there are possible electromechanical application using this specific effect. Okay, let's move now to a last example of the importance of 2D materials and the way we can observe new phenomena in physics. And this new phenomena is the antifocusing effect. So first I will explain how Dirac fermions flow in graphene, and especially through a p-n junction, and we will see that we observe an anti-focusing effect in this case, which is an analogy to optics again, and we will go from simulation to experiment because we have convinced an experimental group in our university to do these experiments in order to observe the phenomena. So the phenomena that I wanted to explain you is, in fact, the electrons, the evolution of Dirac fermions in p-n junctions. So the way you can create p-n junction in graphene is very easy because since you have this Dirac cone, so the Dirac cone is this. So if you take these two cones from the water machine, you have exactly the Dirac cone. So the Fermi energy is exactly at the middle, but if you go down if you move down the Fermi energy, if you n-dope your system, you will have the Fermi energy in your upper cone, and if you move up the Fermi energy, you will get the voltage. In fact, you will get your Fermi energy in your lower cone. So this is exactly the p-n junction that we have here. And in fact, electrons can go through this barrier. And this is very easy to model. So you have to add just this term in the Hamiltonians, which take into account of a certain slope for the transition. Okay, let's suppose now that the slope is extremely abrupt. So this means that d tends to 0 in this case, and well, it's not exactly 0, but it should be at least below the Bragg wavelength. So it's a very abrupt situation. And in this case, in fact, in the case of sharp interface, what you observe in graphene, due to the conservation of the pseudospin, in fact, is that this charge, these Dirac fermions will go through the barrier without filling it. So this is exactly what is called the Klein tunneling. So the Klein tunneling is there is no reflection, it's a total transmission of the Dirac fermions throughout the barrier. However, if you look carefully at the section of the cone, so this is the section of the upper cone, and this is the section of the lower cone here, what you see is that for a certain velocity, for a certain group velocity, you see that the ky components goes on the other side when you go from the upper cone to the lower cone. So you have a reverse of the group velocity of your Dirac fermions. What does that mean? This means, in fact, that you can use this graphene, especially p-n junction in graphene with very sharp transition like this, as a lens. A lens, because, in fact, if you start from this point here with your electrons, you have electronic trajectories that are diverging from this point, and when you reach the p-n junction, suddenly it's refocus to a focus point which is here. Okay? And this is due to the fact that your group velocity change sign. So it's exactly, you have an optical analogy of a metamaterial with a negative index of refraction. And this has been firstly studied by a Russian physicist, which is Victor Veselago. That's what we call that Veselago lens. Okay? This effect has been predicted theoretically first in graphene in 2007 and has been also really observed experimentally in science as well in 2016. So just by putting two gates with different voltage, with different potential, you can create this p-n junction, and if your interface is sufficiently abrupt, you can really observe this focusing of the electron trajectory of the Dirac fermions in the system. Okay, but what we really want to investigate in our case is the fact that sometimes you do not have such abrupt interface in the p-n junction. And this is here the case for when d is proportional to the de Broglie wavelengths. And in this case, what happens is that you have a partial transmission throughout the p-n junction. And it's restricted only to quasi-normal incidence for the trajectory of your electrons. All the other the trajectories are bent but are not really transmitted along the system. So there is no focus point as in the previous case. Okay? So in this case, what we can do is to model a smooth circular p-n junction using, for example, a Lorentzian potential. Okay? So in order to make this junction circular, so you have a Pn, for example, junction here, okay, or Np, it doesn't really matter in this system. And so if you do that using a quite simple tie binding simulation, you can see that in fact the local current that is injected on the left of this p-n junction leads to very small value here around the junction. So you have a maximum that is here just at the center of the p-n junction, so in the center of the Veselago lens, because it's directly connected to a Klein tunneling effect. And you have also two low current density regions which are on both sides of the transport direction of the lens. And this is really what we call the anti-focusing effect in this p-n junction. So you have extremely low value for the local current around this junction. So what happens if you look at a kind of semi-classical electronic trajectory, you have some banding of this trajectory along the p-n junction, and of course sometimes when you have a nearly quasi-incident trajectory which is perpendicular to the p-n junction, then you can cross the system. And that's why you have a maximum here compared to the low value that are on the two sides of the lens. Okay, so we have also looked at different type of potential, and we have clearly shown that in fact this anti-focusing effect is essentially related to the smoothness of this junction. So if we have an abrupt junction, we have only Klein tunneling, because in fact it can go through directly, it's always incident to the junction, so you do not observe this focusing effect, this anti-focusing effect. But if you have more, for example, more abrupt junction than the previous one, you see that the zone where the local current is extremely small, in fact, are shortened compared to the previous case. Okay, so now we have tried also to investigate it experimentally. So we have, as I mentioned, we convinced the group of Benoit Hackens from the University of Louvain to use a scanning gate microscopy technique. So this is in fact the tip of AFM in this case. And in fact it induces, the tip voltage here induce a modification of the charge distribution of the sample. Okay, and if you do that, you can induce conductance change. And since this tip gate is also a local gate which is on top of the sample, you can also map, in fact, the tip-induced conductance change that you produce with the tip. This has been quite well known in the case of 2D electron gas. So when you have electrons that are passing through, for example, a constriction, you can see that with the tip you can, in fact, interfere with the electrons flow throughout this constriction. So this is quite well known for transport in 2D system. In the present case, so what they did is to use a high quality graphene which is encapsulated in between boron flakes. So in order to have a very high quality for the charge carrier, so you have the mobility of the electrons, which is quite important as well as for the hole. And just by coming with the tip of the SGM close to the surface of the sample, you can induce a small local zone that is on other type of doping. So suppose that with the backgate you induce some N doping in graphene, you can in fact induce here a negative potential that will induce a P-doped region in this part of graphene. So this is not exactly the sample that we use, because they had sample with constriction in graphene, so with really small possibility for the electrons to transit from the left part to the right part, and this constriction is about 250 nanometers. So this is exactly the sample that they use to investigate this antifocusing effect. And so in this case there is a narrow quantum point contact which is based on graphene, and which acts as a kind of filter for the current into this constriction. And this is the experimental SGM maps that they obtain in order to investigate the conduction of electron flow throughout this constriction with the SGM. So in fact, at first they introduced a -7 volt potential for the tip, and the backgate is positive. So if the backgate is positive, the system is N-doped. So in this case, this means that if you put a negative potential for the tip, you will have a P zone here, so you have an NPN junction. And when the backgate is extremely high, so you do not have an NPN junction but an NN junction. So this is in fact a decreased of the conductance, so you have a minimal value of the conductance. But when you go to the NPN junction, you see exactly this antifocusing effect. So you have the maximum of the conductance that is here at the center of the constriction, and you have two minimum value of the conductivity on both sides, so along the transport direction. So this is the two antifocusing zone that I have explained before. And if you do exactly the same with holes, so if you impose a backgate which is this time negative, so you have a PNP junction in this case, and you play with the tip now, you have exactly the same. So it doesn't matter if it's an NPN or PNP junction, you get exactly the same. So we try to investigate a tip-induced perturbation which is as close as possible as what they did experimentally with the microscope. And what we did is that we have a quite good comparison of the SGM map, both from the simulation point of view and from the experimental case. So here you see that we have these antifocusing points that are also in the model here, and you have the maximum of the conductance at the central zone of the constriction. Okay, you can play with this again, and with different type of potential, with different, but I don't want to go into many details, and I think that I'm running out of time. So this is the outlook of the third part, sorry. So it's a novel effect which leads to electron antifocusing, which is predicted and also observed by SGM in graphene quantum point contact. So we have high current density that is observed at the lens core, as a direct consequence of the claim to the ring and the conservation of the pseudospin in graphene. We have low current density point contact away from a small circular p-n junction, which is highly sensitive to the junction smoothness, as I show you, and controlling and understanding the fermions is very important to engineer new relativistic electron optical devices, and we expect to find some application for this specific effect in the future. So before ending, I would like to acknowledge my collaborator in this research field. So Benoit Akens, who did the experiment on the SGM that I've just shown you, and my collaborator in the modeling field. So Andrés Botello Mendes, who is in UNAM here, Aurélien L'Herbier, Jean-José Gigian, Simon Dubois, who is also here, and Vietoon Nguyen, and also some funding. And I would like to thank you very much for your attention.
Thank you very much, Jean-Christophe. So we have time for some questions.
Yes.
I don't remember the details about the experimental boron layer. So
Me neither.
no,
I'm
but
joking.
maybe you do know, like the crystalline size, the grains.
Yes.
How big are the grains? Because for example, MOS2 or graphene, you can get a monocrystal that is big enough to, with great paint, but you should be able to orient it in the right direction. For this, I have no idea. Like I wouldn't know.
Yes. So you are speaking about this one,
Yes.
or the hexagonal one. So in this case, the size of the crystals are around, well, let's say it's close to 50 nanometers, especially in the case of the triangular lattice. And in fact, you have indeed a close interaction of your Borophene layers with the silver substrate. And this is why normally probably you could stabilize these 2D materials.
So
and if
in that way you could orient
yes,
it.
in that way. But you have exactly the same in the case of aluminium when you have this hexagonal face of boron for boron, and in this case you have also a very strong interaction with the substrate. So in both cases, and I talked to Mark Ersan about that, it's extremely difficult to extract Borophene from the substrate. They still not really, they are not able to do it for the moment. But it should be very interesting to have access to a pure isolated system in order to check especially the optical or the optoelectronic properties of this device.
And also for the optical Hall effect. So
Yes.
you said that even at 2% strain you can see
Yes.
the effect. But that, would it matter the direction? Like if you're a little off, let's say you're
No,
hitting
you will
40,
observe it anyway, at least
yeah.
you will observe it in the optical Hall
maybe not
conductivity.
that hard.
Well,
We can try.
you have at least to bend your system and also to shine it and also to have access to the optical conductivity. Yeah? So it's, well, if you're interested to understand.
I have a simple question. You show a mean-free path of 100 nanometers for this material.
Yes.
But for example, in silver, the mean-free path is about 40 nanometers, something like that. So how much realistic is this?
This is difficult to answer because we don't have any possibility to measure the electronic mean-free path in this system because the substrate is metallic. So there will be some interaction with the substrate. So it's not really possible actually to have access. But Evan, let's say that a metal, between 10 and 100, you do not see much difference in the transmission. Okay, even if you have only 10 nanometers for the electronic mean-free path in your Borophene materials, you'll still get close to 100% of transmission. So it's not going to play a real key role in the transparency of Borophene. So this we checked that just to be sure that we were not wrong, just by looking only at the interband transition in the dielectric function. But in fact, it does not play really a key role in this system.
when you are calculating the interband and the intraband,
Yes.
are you taking into account the screening effects? Because
No.
yes, that's okay.
No, that's true. Yeah. This could play probably
could play
a more important
yes.
role. Yes, I agree.
Okay.
Yeah.
Is a question related. There is a recent work of Sorella and Tosati, in which they apply a isotropic strain on graphene, and they argue that there is a kind of mode gap insulator which breaks symmetry by analytic antiferromagnetic, that is between A and B.
Yes.
Could be, you think could be possible then to dope this material to try to find, search for superconductivity, high temperature superconductivity? What do you think?
Well, this is an interesting question, but I'm not sure that. Well, first, if I remember the work of Elio Tosati, it's really an isotropic strain. So this is not what we are doing here. Huh?
Oh,
No. In this case, it's really an axial strain that we are doing. Okay. Well, if you dope it, well, I don't know. I do not remember exactly. Is the density of state strongly affected by this isotropic effect of the strain? I don't know. I do not remember exactly how it is affected, but well, I cannot really answer to this question.
Any other question? If not, we thank Jean-Christophe again.